Welcome. All right, so now we're going to be looking at rules for differentiation, finding the derivative of a quotient of two functions, and this is the quotient rule. All right, so I'm going to try to put this in the notes already before I print this out to you, since I haven't printed it out already. But if it's not there, then you're going to add this information. All right? But before we learn about the quotient rule, let's rewrite this, all right, and use what we know to find the derivative. All right, so we're going to rewrite the function f of x equals 2x cubed minus 3x squared plus 2. All right, that means we need to divide each term by x squared. All right, so 2x cubed divided by x squared, that's going to, and you need to write this along with me, that's going to be just 2x. Negative 3x squared divided by x squared is just going to be a negative 3. And 2 divided by x squared is going to be, well, 2 divided by x squared. But we need to rewrite that. Right? So once we reduce, that's going to be 2x minus 3 plus, we need to rewrite that with a negative exponent so that we can use the power rule. So that'll be 2x to the negative 2. All right, so when we use the power rule to take the derivative, right, we multiply the exponent by the coefficient and we reduce the exponent by 1. Right, so exponent's 1, right, so 1 times 2 is 2. If we reduce the exponent by 1, it'll be x to the 0, and x to the 0 is just 1, so that's just going to be 2. Derivative of a constant is 0, right, so I'll just kind of squeeze that one in there just so we can just remind you. I'll put it over here. Right, so the derivative of the negative 3 is 0. And then the derivative of 2x to the negative 2, negative 2 times 2 is going to be a, actually I'm going to just put a negative minus in there instead of a plus, is going to be minus 4x. Negative 2 minus 1 is going to be negative 3, so it's negative 4x to the negative 3 power. All right, so just as Leibniz was the first to publish a proof of the product rule for differentiation, Isaac Newton was the first to publish a proof for the quotient rule of differentiation, using the limit definition of the derivative. Right? And I could go through it, but I don't think it's absolutely essential that we go through the limit definition, but that is where it's derived. And so later on, maybe we could look at that in class. So let's write the rule together, and I have that rule written in there for you. So the quotient rule, right, is going to be the derivative. So u is the numerator, v is the denominator, dv is the derivative of the numerator, du is the derivative of the numerator, and dv is the derivative of the denominator. Right? And so it's going to be v, the denominator, times du dx, the derivative of the numerator, minus u, which is the numerator, times dv dx is the derivative of the denominator, divided by the denominator squared. Right? And so sometimes you can write that in kind of a shorthand. Right? So the derivative, so if we don't put the x in there, the derivative of u divided by v is going to be v, the denominator, times the derivative of the numerator, minus the numerator times the derivative of the denominator, all divided by denominator squared. All right, here's a little mnemonic device that you could use to help you remember the quotient rule. So it's low d high. Right, so low is the denominator, d high is the derivative of the numerator, minus high d low. High is the numerator times d low, derivative of the denominator, divided by low low. So low d high minus high d low divided by low low. That's just a way to kind of remember it. Right? And so just as a reminder, the derivative of a quotient is not the quotient of the derivatives. Right? So fill this in your notes and pause me if you need. On the next page, we're going to use the quotient rule to find the same derivative. You have it at the bottom of your notes. I needed more space. So to show the rule works, let's apply this rule to the function f of x equals 2x cubed minus 3x squared plus 2 that we rewrote and differentiated as a polynomial form above. Right? So we're going to use this one using the quotient rule. Right? So as a reminder, quotient rule, if we're taking the derivative of a quotient, right? It's going to be the denominator times the, derivative of the numerator have a tickle in my throat, minus the numerator times the derivative of the denominator. Yeah, make sure I make my u's and v's look different. All divided by the denominator squared, right? And so let's identify our u's and our v's and our du's and dv's, right? So u, our numerator, is 2x cubed minus 3x squared plus 2. Right? And then I'll write v too. The v is x squared. Right? So now let's take the derivative of each of those. Right? So du dx, it's going to be derivative of 2x cubed is going to be 6x squared. Derivative of negative 3x squared is going to be negative 6x. And the derivative of 2 is 0. The derivative of x squared is going to be 2x. All right, so now let's use our quotient rule. All right, so the derivative, so f prime of x, is going to be the denominator, so x squared, times the derivative of the numerator, 6x squared minus 6x, minus the numerator, which is 2x cubed minus 3x squared plus 2, divided by the derivative of the denominator, 2x. All divided by the denominator squared, so x squared squared. And yes, you must simplify. All right, so x squared times 6x. There you go. By the way, the only thing you could factor out is an x, and it's really hardly worth the effort. So if I could factor out a binomial, that would be worth the effort. So let's just distribute and combine like terms. X squared times 6x squared is going to be 6x to the 4th. X squared times a negative 6x is negative 6x cubed. And then we have minus 2x cubed and plus 3x squared and minus, oops, excuse me, I forgot to multiply. Never mind. Forgot all about Mr. 2x here. All right, so we're going to multiply. I'm going to actually put this over here so I can remember to multiply both the negative and the 2x. All right, so 2x cubed times negative 2x is going to be a negative 4x to the 4th. I tend to reverse the order of those, by the way. If the second one is nice and small, and it's going to be what I'm distributing. So 2x, negative 2x times negative 3x squared is going to give me a positive 6x cubed. And then negative 2x times 2 is going to be a negative 4x, all divided by x to the 4th. All right, so now let's combine our like terms. F prime of x is equal to, so that's going to give us now 2x to the 4th. And then we've got, well, the 6x cubes are going to cancel out. And then we have negative 4x, that's it, divided by x to the 4th. Now we should reduce that. So f prime of x is equal to, so everybody's got an x, everybody goes down by 1x. 2x cubed minus 4 divided by x cubed. All right, let's see if that's what we got. We had to do a lot more work here, huh? Well, on a problem like we did in the opening, I would never use the quotient rule. I would simplify. However, we're going to come across lots of problems where you would have to use the quotient rule. All right, so we got 2x cubed minus 4 divided by x cubed. And here we have 2 minus 4x to the negative 3. Is that the same? Well, let's write it down here. Let's move this one over. So f prime of x is 2 minus 4x to the negative 3. All right, so on the other page we had 2 minus, and actually we should simplify that, by the way. So technically we should have make this, let's fix this. Don't leave the negative exponent. 2 minus 4 divided by x cubed. All right, so now let's go back to this one over here, right, where we have 2 minus 4 divided by x cubed. Is it the same? Well, if we were to simplify 2x cubed minus 4 and divide those both by x cubed, we would have 2 minus 4 divided by x cubed. So yes, they are the same. We got the same answer with the quotient rule as we did when we simplified. So you can see in this example, simplifying would be better, right, than using the quotient rule. But we're going to get to examples where we need to use the quotient rule, right? But I wanted us to start with something that we could do 2 different ways so that you could see how the quotient rule works. Let's find the tan. Now, so here we have a problem where we couldn't reduce, right? You can only reduce by if you can cancel out an entire factor, or if you've got just a single term in the denominator. We want to find the equation of the tangent line drawn to the graph of g of x equals 2x minus 1 divided by x plus 3. As a little reminder of the quotient rule. Right, so our derivative of a quotient is the derivative of the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, all divided by denominator squared. All right, so u is 2x minus 1, v is x plus 3. Mighty easy derivatives, by the way. The derivative of 2x minus 1 is 2. The derivative of x plus 3 is 1, right? The derivative of x is just 1, and the derivative of the constants are 0. Right, so we're going to have our derivative, or this is g of x. So we're going to have g prime of x. Right, so g prime of x is equal to, right, so the denominator, so that's x plus 3, times the derivative of the numerator, so that's times 2, minus the numerator, which is 2x minus 1, times the derivative of the denominator, which is just 1, all divided by the denominator squared, so x plus 3 squared. By the way, I never square that denominator out. There's no reason to. It's not like you're combining with any of the terms. All right, so 2 times x plus 3 is going to give us 2x plus 6. And then we'll distribute the negative, because multiplying by 1 isn't going to do anything, minus 2x plus 1. All divided by x plus 3 squared. And now we'll just simplify that. G prime of x is equal to, well, we're going to have a 7 divided by x plus 3 squared. And there's our derivative. We want to find the equation of the tangent line when x is negative 2. All right, so we'll need to evaluate our derivative at negative 2, and this will give us the slope of the tangent line. I have to stop and give myself a drink of water so I stop coughing. Maybe after this question. So that's going to be 7 divided by negative 2 plus 3 squared, which is 7. Negative 2 plus 3, that's just 1 squared, so that's just 1, which is 7. That's the slope. We need to find the y-coordinate, so we need g of negative 2. So that's going to give us 2 times negative 2 minus 1 divided by negative 2 plus 3. Right, so negative 4 minus 1 is negative 5, and that's negative 2 plus 3 is just 1. So negative 5. Right, so this is the y-coordinate. That means the point that we have is -2, -5, and now we can write the slope, we can write the equation of the tangent line. And that's going to be y plus 5 equals 7 times x plus 2. And then let's just isolate y. So y is equal to 7 times x plus 2 minus 5. And yes, we could multiply it out if you want. We could make it 7x plus 14 minus 5. So that'd be 7x plus 9. Right? You want to put in slope-intercept form now, so it works just fine. That's all there is to this one, right? We find the derivative, we plug in our x value, our x that we're given, so that we can find the slope at that point, and then we just find the y coordinate by plugging that same value into the original function, and then we can write the equation of the tangent line. All right, let's do another problem. I'm going to try not to cough. We're going to use the quotient rule to derive the formulas for the remaining trigonometric functions. We'll rewrite each function in terms of sine and our cosine and differentiate using the quotient rule. All right, and that's how these formulas are derived. All right, so if you remember tangent, right, if we use our the quotient rule, this is the quotient rule for trigonometric functions, right, not the quotient rule for finding derivatives, but the quotient rule for tangent is that tangent is equal to sine theta over cosine theta. I started to write a C and it came out all funky looking. All right, so we're going to take the derivative of sine theta cosine theta. Now I don't have the room here to write the quotient rule out, so just remember to look in your notes again. All right, so our derivative, right, so we're finding f prime theta of sine theta cosine theta. All right, so u is sine theta, and the derivative of that is going to be cosine theta, and that thing there is supposed to be a theta, and I don't know what happened to it. I'm not what happened right there, but our denominator is cosine theta, and the derivative would be negative sine theta. We learned that a few lessons ago. All right, so our derivative is going to be the denominator. So it's going to be cosine. Actually, I'm going to move it down just a little bit, so I have a little bit more space. It's going to be, and this is in your notes, it's going to be cosine theta, and then times the derivative of the numerator, so times cosine theta minus the numerator, sine theta, times the derivative of the denominator, negative sine theta, all divided by cosine theta squared, so cosine squared theta. All right, so f prime of theta, let's simplify this. Cosine theta times cosine theta, that's cosine squared theta. Sine squared theta times a negative sine squared theta times a negative sine squared theta is a positive, excuse me, a negative sine theta times a negative sine theta, I'm thinking ahead, is a positive sine squared theta. I kept saying sine squared instead of just sine theta. All right, and that's all divided by cosine squared theta. Well, cosine squared theta plus sine squared theta, this is Pythagorean identity. Right. Right there. This one here, by the way, was the quotient rule for tangent. It has nothing to do with quotient rule for derivatives, right? All right, so Pythagorean identity, cosine squared theta plus sine squared theta, that's 1. So f prime of theta is 1 over cosine squared theta. Let's use a reciprocal identity. So cosine theta, who's its reciprocal? Well, its reciprocal is sine squared theta. So that means the derivative, that's theta, of tangent is secant squared theta. That's the derivative of tangent. Right? So put that in your notes so you know where it's derived. And the other thing is if you ever forget it, right, if you just change tangent theta to sine theta over cosine theta, it wasn't that much work. You can get the derivative. Better than guessing if you don't remember what it was. All right, and let's do the same thing, but with cotangent. Well, cotangent is reverse. It's cosine theta over sine theta. Right? And so, oops, that thing's a theta. Right? So that's the quotient rule for a quotient identity, not quotient rule. Keep calling it rule. Thinking of what we're doing now, quotient identity. And that is supposed to say identity. Identity. All right, so quotient identity there, and a quotient identity there. I don't have to write it twice. All right, so U is cosine theta. Derivative of cosine theta is negative sine theta. The denominator is sine theta. Derivative. Oops, that's supposed to be a dv. It looks like a u. Is cosine theta. All right, so I'll write it over here. So f prime of theta is, all right, so the denominator, sine theta, times the derivative of the numerator, times negative sine theta, and then minus the numerator, cosine theta, times the derivative of the denominator, cosine theta, all divided by the denominator squared, sine squared theta. All right, so let's simplify that. So f prime of theta is sine theta times negative sine theta. That's a negative sine squared theta. Negative cosine theta times cosine theta. That's a negative cosine squared theta all over sine squared theta. You cannot reduce, by the way, things that are added and subtracted, just in case somebody had that idea in their head. That'd be really, really wrong. Now let's factor out the negative 1. They're both negative. So if I factor out the negative 1, we have sine squared theta plus cosine squared theta all over sine squared theta. And we just know from a moment ago that's a Pythagorean identity. So f prime of theta, right? So this whole thing here just equals 1. So that would be negative 1 times 1, or negative 1, divided by sine squared theta. Now, we're going to use a reciprocal identity again. So now, what is sine theta the reciprocal of? Well, that would be cosecant. So the derivative for cotangent is going to be negative cosecant squared theta. Ta-da! And boxy that. And we have 2 done. We got 2 more to go. All right? So now we've derived, using the quotient rule, 2 of the trig derivatives. Here's our last 2, secant theta and cosecant theta. All right, so for secant theta, we're going to use a reciprocal identity. Man, oh man. Let's write it over. Well, I want to write it over there so I could use it for twice. I guess that looks a little better. It's reciprocal identity. All right, so secant theta, the reciprocal for secant theta is cosine. All right, so f theta is, f prime of theta is equal to 1 over cosine theta. 1 over cosine theta is secant theta. Right? And secant theta is 1 over cosine theta. All right, so u is 1. The derivative is 0. V is cosine theta, and the derivative is negative sine theta. All right, so we're going to have the denominator. Right, actually, excuse me, that doesn't get the, that's just, we haven't taken the derivative yet. That's just an f theta. All right. F prime theta is equal to the denominator, cosine theta, times the derivative of the numerator. Right, so that's going to be 0. And then minus, and I'm running out of space, so let's maybe move it down a little bit. I've got lots of space below, so no worries there. All right, so the numerator, which is 1, times the derivative of the denominator, which is negative sine theta. All divided by the denominator squared, cosine squared theta. All right, well, anything times 0 is 0. All right, so that's just going to be 0. And this will be plus, because there's a negative and a negative. So 0 plus sine theta divided by cosine squared theta. All right, so, but we're not done yet. Let's simplify this a little bit. Oops. All right, so let's not have we don't want a derivative that's got a denominator. No denominators. All right, so sine theta divided by cosine squared theta. Well, what is cosine squared theta? All right, so 1 over cosine squared theta, I think that's just equal to secant, right? Just want to make sure I have the errors here, right? Okay. All right, so let's replace that. Actually, no, I don't want to do it that way. Never mind, never mind. Yeah, that's true. I don't want to make both of them. Sorry. I think for a moment. It's late here. It sounds spooky. I was distracted by spooky sounds. This place makes spooky sounds at night. So what, sine theta over cosine theta, that's tangent theta. And 1 over cosine theta, because I don't want any squares. 1 over cosine theta, that's going to be secant theta. So if I rewrite this as sine theta divided by cosine theta times 1 over cosecant theta, I can change this to tangent theta secant theta, and that's the derivative of secant theta. There we go. All right, one more to go. All right, want the derivative of cosecant theta. Again, we're going to use a reciprocal identity. So just go like that, reciprocal identity. So our cosecant theta is the same as 1 over sine theta. Right? And you might be thinking, why did we use a reciprocal identity? Because we know the derivative of sine and cosine, and you don't know the derivative of cosecant. All right, so u is 1. The derivative is 0. V is sine theta. The derivative is cosine theta. All right, so now we have f prime of theta, what can I make a theta, is equal to the denominator. Right, so that's sine theta times the derivative of the numerator, that's 0, minus the numerator, which is 1, times the derivative of the denominator, so that's cosine theta, all divided by sine theta squared. All right, so anything times 0 is 0. So f prime of theta is equal to 0 minus cosine theta divided by sine squared theta. So that's just going to be negative cosine theta divided by sine squared theta. And I'm going to split this up again. I don't want any squares. So f prime of theta is, let's put negative cosine theta and sine theta together, and then times 1 over sine theta. Cosine theta over sine theta, that's going to be cotangent. So f prime of theta is negative cotangent theta. 1 over sine theta, that's going to be cosecant theta. And there you have it. There's the derivative for cosecant theta. And now we have all 6 trig derivatives. Let's take a look at them all together. Make sure you have this in your notes. Make sure you know how it's derived. All right? And if you need to, pause. All right, so the derivatives of the trig functions. Derivative of sine x is cosine x. Derivative of cosine x is negative sine x. Derivative of tangent x is secant squared theta. Derivative of, I'm going to go across there. Derivative of cotangent x is negative secant squared theta. And then we did derivative of secant x was secant x tangent x. And derivative of cosecant x is negative cosecant x cotangent x. Now I write them in the other direction. I usually write cotangent first and then cosecant, but that doesn't matter, right? Either way, right? So you can write it this direction, or it's the exact same thing if you write it negative cotangent x cosecant x. For, I guess it doesn't show up real well, does it? I guess I'll write in red. So for purposes of deriving it, I did it the other way, but it doesn't matter which way you write it. People usually write it this way only because cosecant, they put cosecant first. Right? But this is the same whether you write them this way or the other way. So now let's write them both ways. All right, so tangent x, tangent theta, secant theta, or secant theta, tangent theta. When I was deriving them, to me it seems simpler to think of sine and cosine together, and then there's the leftover one. And then the same thing here. But either way, it's the same thing, right? Because multiplication is commutative. And it doesn't matter which way you multiply. All right, so in the next podcast, we're going to be finding all kinds of derivatives, including derivatives of trig functions. All right, bye for now.